Grace. How did I only end up with one? That's okay, don't worry about it. I at least want to go over some of the things from there. Anyway, as you can see, this chapter 55 is about ecology, and it's also about biogeochemical cycles. And I'm not going to really test you probably on this turnover time, but it was a part of the chapter, and if we had lots of time to study it, we would probably get into that. So concept 54.5.4, biological and geochemical process, cycle nutrients in water and ecosystems. And we kind of went over that a little bit from the photo of the PowerPoint yesterday we started. When the organism dies, the atoms in its body are returned to the atmosphere, water, and soil by decomposers, which are so necessary. Just imagine if we had decomposers. We had no fungi and prokaryotes that return things back to the soil. I mean, nature has its own recycling system. Plus, we also have scavengers that, like the vultures, roadkill. The vultures, the buzzards will come in, and they will. We really don't want all these laying around all the time. Do you think they have a good sense of smell?
Not so much.
If you were in the business of being a scavenger and you're eating dead roadkill, would you really want to have a great sense of smell? Probably not. But you have a very good sense of sight. Birds typically have a good sense of sight. Okay, so. All right, so it's going to take us through the cycles, and then it's going to get into the restoration, ecology, situation, and bioremediation, and biological augmentation. Okay, now, this is what I put on Blackboard yesterday. I actually took some of the things from PowerPoint. I didn't put it into a PowerPoint, but I put it into a Word document. Two actual columns. So, I don't know, you might want to print those off instead of printing them all PowerPoint. Okay, again, I think we went over this. I think we went over, these are like trophic levels, aren't they? Trophic feeding levels. Okay. Some terminology you really should know. Eutrophication. When you have fields, agricultural fields, and if they add fertilizer to the soil or other chemicals that are added, they can run off into streams. When they have heavy rains and so forth, you can have runoff. And like detergents, back in the 70s, 80s, detergents were manufacturers were made to change and take some of the nitrogen out of their detergents, because once they got to the public water system, they would cause algal blooms. And so an algal bloom is where algae just go nuts and they get algae everywhere. Or if you're around a pond, you cause seaweed. And those actually are not good for the ecology of the pond or lake. You would think since they're photosynthesizers that would be good, but the problem is that those are going to die at some point, and when they die, they're going to go to the bottom, and it's going to take a lot of oxygen to decompose them. So that leaves less oxygen in the water. Eutrophication is which can lead to a loss of most fish species because there's not enough oxygen left in the lakes or streams. Phosphorus also limits cyanobacterial growth, which is blue-green we used to call it blue-green algae, it's now called blue-green bacteria, more often than nitrogen. So phosphorus and nitrogen getting into streams is not really a good thing. So eutrophication is not a good thing. So phosphate-free, this has led to the use of, I shouldn't have said nitrogen, I should have said phosphate, the use of phosphate-free detergents. Okay, so various adaptations help plants access limiting nutrients from soil. We talked about mutualistic associations between bacteria, prokaryotes, and roots of plants. Start coughing, I know I am. Allergies starting already?
Yep.
Yep.
Equals on Monday.
Many plants form mutualistic with mycorrhizal fungi. I think we mentioned that before. These fungi supply plants with phosphorus and other limiting elements. So these additional growths on the roots of the plants help them to get some of the nutrients that they need. And roots have root hairs, little fuzzy stuff, that increase the surface area. And many plants release enzymes that increase the availability of living nutrients. In other words, stuff in the soil needs to be broken down. The enzymes help to break it down to some extent. Trophic efficiency and ecological pyramids. Remember, trophic are the feeding levels. We are heterotrophic. Plants are autotrophic. Okay, percentage production transfer from one trophic level to the next. This is where we talked about before. It's usually about 10% of the energy is transferred from one feeding level to the next, but it can vary. Trophic efficiency is multiplied over the length of the food chain. So you end up with like 0.1% of the original energy that was in the nutrients that would happen to be in the producers. So this is something I wanted to add. I'm not sure if I've done this before, but I always want to. This is a practical thing for you. You're probably going to own a home at some point, or you're going to be friends with somebody who does. And so you're going out to look for fertilizer for some of your trees and shrubs and various things. And you're faced with three numbers. Whether it says 11, 11, 11, or 5, something, something. And what you need to know is what those numbers mean on a fertilizer container. And the first one stands for nitrogen, the percentage of nitrogen that's in there, and the second number, let's just go to, I think I've got it. Get out of place. Okay, first of all, before we get to the actual bag numbers, let's just go over the nutrients needed for plants. Extremely important for the greenness of the plant. Leaf and growth are dependent on nitrogen. Phosphorus is critical in the germination and growth of seeds, flowers, fruit, and roots. So during the flowering season, you're going to need a little more phosphorus. That's why if you look at fertilizers, you will see they vary. And like if you get that liquid stuff from Miracle-Gro that you put on the end of a hose, you have one for blooming plants, and then you have one for regular plants, because you'll have more phosphorus if it's a flowering season and you're wanting to have good flowers. The other two, although there's only one more that's listed on the fertilizer as a number, the potassium promotes the hardy disease-resistance growth. So potassium is helping to fight diseases. Of course, it depends on the genetics of the plant that you're, whether or not they're real disease resistant or not. But potassium helps with their disease protection. Calcium is a vital component in cell walls of plants. It's calcium is very important also to animals as well. You know, muscle contraction for bones and teeth, for a lot of other. Nutrient limitations and adaptations on a more local scale. A soil nutrient is often the limiting factor, since nitrogen is the most cursed on the fertilizer container. Phosphorus can also be a limiting nutrient, especially in older soils. And it starts to talk, where did I put them? I don't know, I guess I got these pasted up. I guess I got these separated. I'm going to go to the next page, page 3. Fertilizer labels have three bold numbers. The first number is the amount of nitrogen. The second number is the amount of phosphate. And the third number is the amount of potash. They call it potash. And it's really potassium. Remember, potassium is a K, whereas phosphorus is a P. Okay, so these three numbers at the top here, NPK is really what it stands for. So if it's as you do phosphorus and also potassium. So it's nitrogen, phosphorus, potassium, in that order for your numbers on the fertilizer bag. Okay, let's go back to let's go by geochemical cycles. We went into a little bit yesterday. Life depends on recycling chemical elements. Nutrient cycles involve biotic and abiotic components and are often called bio-geo. Geo means earth, bio means living. Geochemical cycles. Okay, this example up here. Okay, if you have like 4 different reservoirs, reservoir A has organic materials, which we do carbohydrates, lipids, proteins, nucleic acids in living things. Organic materials available as nutrients. You have living organisms and detritus. You can also have some that become fossilized, which is to the 2 o'clock, 3 position up there. Organic materials unavailable as nutrients, they actually get compressed in bogs, become peat, and from the Carboniferous period, way back when they became coal and oil. But mostly, and of course, most of our fuels for running of our automobiles and tractors and other things is the burning of fossil fuels. That's why they call them fossil fuels, because it's from the fossilization of organic matter. And particularly a lot of big gymnosperms back in the Carboniferous period. Reservoir C has inorganic materials available as nutrients. So you have the atmosphere, the air, you have the water and the soil, the mixture. Over here, inorganic materials unavailable as nutrients, and minerals and rocks. A rock is made of different combinations of minerals, which are really different combinations of elements. And like quartz, you have a lot of silicon, and you have a lot of other stuff in it, and so it's kind of unavailable. You have, though, from weathering and erosion, you can have the breakdown of some of these elements then going over here where they become available, or from here to here, the formation of layered rock sedimentary, like sandstone, limestone. Here's your typical pyramid, or well, see, it kind of goes like this. All right, where these are trophic niches, feeding levels. We have the sunlight. You have the primary producers, which are the plants.
whoever eats the plants, and then whoever eats that one, and then whoever eats this one. This is in joules, and joules is an energy amount. Those of you in physics are well aware of joules, I'm sure. About 0 point, so from here to the original, it's about 0.1% is captured of the energy is actually captured at the tertiary level from a producer. And then you've got some other situations that this is most ecosystems. This is the biomass in grams per meter squared. Trophic levels of a aquatic ecosystem, primary consumers and primary producers. So phytoplankton versus zooplankton, and the dry mass of those. So biomass, aquatic ecosystems may not acquire as much per unit, but because there's such a large surface of water in the world, it generates a large biomass as well as energy. Now let's go back to 3. This is your typical water cycle that you've probably been given through every science class you ever had, particularly through elementary school and up through high school. The evaporation of water, forming of clouds. You have plants transpire, and so we perspire, plants transpire, transpiration, which evaporates water, moisture into the air. And then you have precipitation over land, then the percolation, the running of the water through the soil. You have runoff and groundwater, and this whole water cycle. Water is essential to all organisms. Liquid water is the primary physical phase in which water is used. The oceans contain 97% of the biosphere's water. Think of that, the oceans contain 97% of the biosphere's water. 2% is in glaciers and polar ice caps. Well, melting. So it's going to raise the 97%, and then 1% is in lakes, rivers, and groundwater. So these processes move the water as previously described. The carbon cycle. Okay, carbon is the backbone to all organic compounds. Remember, it has 4 bonding sites. Photosynthetic organisms convert CO2 to organic molecules, such as glucose, to be used by heterotrophs. Carbon reservoirs include fossil fuels, soils, and sediments, solutes in the oceans, plant and animal biomass, the atmosphere, and sedimentary rocks. Okay, here's really an example of the carbon cycle. Just kind of study that, get a chance. Talk about the nitrogen cycle as a component of amino acids, proteins, and nucleic acids. The main reservoir of nitrogen is the atmosphere, then 2. Here's a big one to remember. Plants have to have nitrogen, but they can't use N2. And the main way that they get a usable form, a chemical form, is through prokaryotes, nitrogen-fixing bacteria in the soil, converting it to either nitrites or nitrates. Okay, so that's definitely a limiting factor with nitrogen. Okay, so organic nitrogen is decomposed to NH4 by ammonification, and NH4 is decomposed to the nitrates by nitrification. Denitrification is not a good thing. It's where you actually reverse it. It goes backwards. And bogs can do that. Whether it's waterlogged, it becomes anaerobic. Did you have a question?
You said about plants outside of nitrogen, but they can't use it into.
Yes, they can't use regular atmospheric oxygen or nitrogen. And so they have to have a chemical form, either nitrates or nitrites, which bacteria are usually intermediate to convert into something that's more usable. Ammonia in some cases is also usable. But we've got all this nitrogen in the air, but phosphorus cycle. Phosphorus is an ATP, right? Adenosine triphosphate. Is phosphate in DNA? Yes. Sugars, phosphate, on the sides of the ladder. Is there a phosphate also in RNA?
Yeah.
Yes. So those are the main reasons why phosphate is so important. And it talks about that. Here's some decomposition and so forth. Okay, as I said, there are, you actually get to a point, restoration, please know what restoration is. Ecology seeks to initiate or speed up the recovery of a degraded ecosystem. There's an example. Like if you have a piece of land that's totally stripped for whatever reason, this is the restoration of it. In the county that I grew up in, the whole eastern side of the county was stripped coal mines. And they actually went in and did restoration, and now they've got parks and things over there where they replanted from the strip mining. Please study that, because we're not going to have a chance to talk about all of this on Monday. We're going to 56. So between, like I said, between your chapter outlines provided by Grace and Brittany, 55, 56, and this new piece of study material, please know your ecology so that we can do more reviewing on Monday. Do some reviewing on Monday. Okay, thank you. Have a nice weekend.